Hello, I am Arun Gitu, and in this video, we will discuss three topics. One, how to optimize master production schedule. Two, demonstrate the use of Excel solver for optimization. And three, demonstrate how optimizing each sub-process separately does not optimize the entire supply chain. Before that, a quick primer on master production scheduling, which I will refer to as MPS going forward. MPS is a statement of planned future output. It's a statement of how production is going to meet forecasted demand while working within resource constraints. MPS output, depending on the sophistication and maturity of the process, may be a production plan based only on forecasted demand without considering available capacity, available inventory, etc. This is also called infinite capacity planning. Second level of MPS output is where the production plan is based on capacity, inventory level, order backlog, and uses user input to determine which products to be manufactured in case demand cannot be met by available resources or with available resources. This is sometimes also called rough cut capacity planning. And in the most sophisticated case, not only are capacity, inventory level, and back order, etc., are taken into consideration, but also goals for revenues, working capital, etc., are taken into consideration, and an optimal production plan is output or produced. This is normally achieved using advanced planning systems or APS. Now, MPS is deep waters, and here we are just exploring what is possible. Additionally, the most sophisticated MPS needs a lot of support to be truly optimized. Support in terms of granular and accurate data, accurate forecast, evolved process maturity, and consistency. Let's first look at a series of simple examples in Excel to understand what is infinite capacity planning and see various heuristics in action that will try and reduce total cost, which is just a sum of holding cost and setup cost. Here we have 10 weeks of forecasted demand. The numbers in green are the demand forecast. We need 3,000 units in week 1, 3,100 units in week 2, and so on. Since production is normally frozen for 2 to 3 month time period, it makes sense to assume that these numbers are firm and the widgets in these numbers need to be produced. For simplicity, let us assume that the lead time for making these widgets is 0. In the later examples, we will have manufacturing constraints, non-zero lead times, components having non-zero lead time, holding costs for components, ordering costs for components, etc. But even with all of these, our model here will be less complex than almost all production environments, but good enough to understand what happens under the hood in a commercially available advanced planning system. And number three, our setup cost to have production is 1,200 and it takes 10 cents to hold a widget for a week. Now, if we make all 29,600 units at the beginning of the 10-week period, we will incur setup costs once and holding costs every week for the balance of the inventory. Now, let us see if we can do better with another strategy. Here, we now have what is called the chase strategy. We make what is needed when needed. This is also called made to order. Here, we have no holding cost, but setup cost for every period. And with the setup and the holding cost numbers that we have here, it's better than the previous single production run strategy, whose cost was 14,000 plus. Now let us see what the EOQ strategy looks like in the next tab. Here, using average periodic demand, holding cost and setup cost, we can calculate EOQ amount or economic order quantity to manufacture. So here the quantity to manufacture is fixed, but when to manufacture varies. So if we use EOQ of 8,249, our total costs are 8,539, which is less than the chase strategy. Please note that in month 9, I changed the quantity to 4,313 since I wanted to leave no unused balance at the end of period 10 to be consistent with all the other strategies that we have been using. To reiterate, what we are doing here is trying to find the lowest cost production schedule to satisfy demand, and we are using simple heuristics for this. Now let us go through one more heuristic before we use Excel solver to find the optimum production schedule. Here, we produce every alternate period to satisfy demand. Or in other words, when to manufacture is fixed, but quantity to manufacture is varying. Here, our costs are better than before. But we should be careful here. It is not that the periodic production run is better than EOQ or any such thing for all setup and holding costs. It's just that with our holding cost and setup cost, which is 1,210 cents or the other way around, our demand periodic production run is better. But given different demand, holding costs, and setup costs, other methods may produce lower overall cost. Let us see that by making the change to holding cost. And now let us see which heuristic produces the lowest cost. So I changed the holding cost from 10 cents to 1 cent. And then here, the single production run is 2,509. Chase is 12,000. EOQ is 3,473. Periodic production run, which was the lowest, is now 6,149. So now single production run is the best. So our strategy of producing the lowest cost depends on our demand, our setup cost, our holding cost, and all other constraints that may be in the picture. So that is why it is these heuristics, they may produce by trial and error a near optimal solution, but for optimal solution, we need a different strategy. Now I have reset our holding cost back to 10 cents per widget per week. And let us look at these numbers again. We have, as before, the periodic production run having the lowest cost. Next, let's look at how optimization will actually decrease costs. Here, we have the same setup as the previous tabs, but we have extra rows and columns for solver to do its stuff. Also, if you want to explore solver, it comes bundled with Excel. So if you have Excel, you have solver, though you may need to enable it before being able to use it. So getting back to this worksheet, let's run solver. And so what we are trying to do here is to minimize this total cost by changing these cells in yellow, which is basically saying, okay, you tell me what is the most efficient production plan. And every time we produce, we need to make the setup equal to 1 so that, our setup costs are taken into account. And there are other few things, but I think that will be going too much deep into Solver. So let's see what Solver does. So here we go, and it says, yep, it found a solution. And we say, okay, close. And the total cost is 7,120. And if you look at our previous case, our most efficient or the lowest cost was 7,490. So this solver produced what is the most or the optimal solution. And for these kinds of problems called the fixed planning horizon problem, wherein we are planning for a fixed horizon, this is guaranteed to give us the optimal solution. So far, we saw heuristics and optimization techniques used for what we called infinite capacity planning. Now, let us introduce a constraint to model a simple rough cut capacity planning scenario. We will introduce a constraint here that we can only manufacture 10,000 units a month or a week, or 10,000 widgets every week. Adding constraint should increase cost since the system has to now work around that constraint. So if you look here, the optimal solution in period 4 or week 4, we manufactured 11,600 widgets. Now, because we have set the maximum capacity to be 10,000, it cannot manufacture 11,000 plus as it did in the optimal solution. It has to work around it, and therefore the cost should be more. So let's see what happens now when we run this. It found the solution, and so let's close that and let's see what it said. See, last time here, it manufactured 11,600. But since we have said 10,000 is the max, it rearranged the production schedule to produce 6,300 here and 8,500 there. And therefore, the cost has gone up as we predicted, 7,120 to 7,140, because this is the optimal solution with the constraint, and this is the optimal solution without the constraint. So to recap, we have seen how to use Solver to optimize MPS. And we have also seen how we can use simpler heuristics to come to a near optimal solution. We need to remember that the goal of MPS is to have a feasible solution. That is, a solution that satisfies all the constraints, even if it is not optimal. The step above that is to find a feasible solution that is also optimal. In the example, our solution was optimal since it was minimized the total cost of ordering and holding costs, which we set as the goal. In real production MPS, there would be many more constraints and many more costs. For example, the cost of ordering raw material, cost of holding these raw materials, transportation costs, etc. But the MPS goal remains the same, which is to find a feasible solution, and better yet, find a feasible and optimal solution. And also remember that the optimal solution is only as good as the data that it is based on. Here, we have the same demand forecast, but we have added a bit more complexity to come closer to what an advanced planning system would model. We added purchasing costs to manufacturing. Actual APS would add transportation cost and other supply chain costs. Before I continue, let me start this process of finding the optimum solution because it takes a minute, and I will then talk about what are the new constraints and costs that we introduced. So let me go here, open up Solver, and then what I'm saying here is I want to minimize the total cost of manufacturing and purchasing. So let me start this here, and this will keep chugging along, and let me then continue about the added constraints. So we now have the widget being composed of 3 sub-assemblies, and for simplicity, they have all the same lead time. The lead time to assemble the widget is 1 week now. Previously, it was 0. The lead time to procure the sub-assembly from an outside supplier is 2 weeks. The ordering cost for the sub-assembly is $1,000, and the holding cost for the sub-assembly is a tenth of a cent per week. Also, we added the constraint. Okay, this is found. Let me say okay to that. So we also have the constraint that we cannot order more than 29,600 sub-assemblies in a week. And we still have the manufacturing limit of 10,000 per week. So now let's see what Solver has done. Close. And what it has done is it says the total optimal cost, minimized cost for both manufacturing as well as purchasing is 10,244. And what is of note here is that the cost for manufacturing has increased from 7140 to 7190. So when it tried to minimize the total cost, it increased the cost of manufacturing. And this is an important point, which I will talk about in a bit more. To reiterate what happened here. In trying to minimize total cost, the solver actually increased the cost of manufacturing from 7140 to 7190. What this seems to be telling us is if we optimize each department in isolation, then the organization as a whole is not optimized. Or in other words, we are leaving money on the table. Let us see this in action now. We have the same setup, and I am now minimizing manufacturing cost by itself. So let me do that in Solver. Go here, Solver, and then I'm saying instead of minimizing the total cost, I am saying minimize the cost of manufacturing, which is R11. So I'll let it fly, and it says, okay, the cost of manufacturing or the optimized cost of manufacturing is 7140 as before. Now, let us minimize the cost of purchasing, leaving the manufacturing cost as is. Let me make changes to the solver to do just that. I'm saying do not touch rows 12 and 13, which are the manufacturing rows. So 12 and 13. So that is 13. I delete that. And then 12. I think I messed up. I I should have done that here. Let's see if this works. Don't change anything in 12 and 13. Right. So let's say, and then minimize. We want to minimize the cost of purchasing, which is R19. So let's do that. Let's see what happens. Okay, close. And then so it has left the manufacturing alone, and it says that the cost of purchasing, if optimized by itself, is 3144 and a total cost of 10,284, which is the sum of these two costs, manufacturing and purchasing. Now, if you were to look at the previous screen, it was the total cost was 244 had we optimized the whole supply chain together. In this case, in this model, the supply chain consists of just manufacturing and purchasing. So the lesson once again is optimizing in total is better than optimizing each department in isolation. If we were to optimize each department in isolation, we'll be leaving money on the table. Let me recap the two main points of this video. One, optimizing in isolation is suboptimal. Optimizing the entire supply chain is more complicated, but more rewarding too. And second, if we want to optimize MPS in isolation or not, our data needs to be complete and accurate. Otherwise, we will have too much or too little inventory, and we will find ourselves making continual changes to the production plan. And these setbacks will reduce confidence in the process. And instead of optimal scheduling, we may end up doing ad hoc scheduling. So my recommendations for making MPS truly beneficial are: first, try to get the best possible data on forecasts, capacities, and costs. For example, having a robust S&OP process involving key personnel from sales, marketing, operations, and purchasing so that we have good demand forecasts. Have consistent data flows between HR systems and production planning systems so that availability of personnel for scheduling is current. Similarly, maintenance schedules should be readily available in the system. And also, data on ETAs for purchases from suppliers should be current and readily available so that the system can look at all the resources available to schedule optimally. Actually, I have a couple of videos in this playlist that addresses automation of purchase orders to suppliers and automation of PO follow-ups that helps suppliers help us. And so my second recommendation for making MPS beneficial is changes in forecast are inevitably going to happen, even within the frozen time window. But by having good data in the system readily available, it'll make it easier to rerun the schedules and adapt quickly and efficiently to the changes. This gets me to the end of this video. If you like this video, please like and subscribe. And if you have any questions or comments, please leave them in the comment section below and I will be happy to answer. Thank you.